This week, our focus, Chapter 4, dealing with regression. The first part for this week is linear regression, and for next week, the focus will be on multiple regression, still from the standpoint of Chapter 4. What I want to go over in the, maybe next 4 or 5 minutes is the focus in on linear regression. And to do that, I will use the data here, whereby we have torus, which will be our independent variable, and ridership is our dependent variable, just a linear expression. And when we talk about linear expression or linear regression, we're just talking about one independent variable, also referred to as a predictor variable. So in this case, we are saying ridership is dependent upon the number of torus that we have for whatever we're trying to come up with. But we're just saying ridership. So ridership is dependent upon the number of torus that we have, say, for a particular event or going to a particular place. So from this data, and we are using just Excel, regular Excel. I'm not talking here about Excel QM, but I'm just talking about our regular Excel software. So with the data, we'll come up with this kind of results. This is what we refer to as our summary statistics page. And you can see is that, in other words, we have really kind of, you might three areas. We have regression statistics that focuses on R squared, and that's our coefficient of determination, and I'll talk about that shortly. We have analysis of variance, and then we just have, from the standpoint of really the crux, and the crux here in this particular section is dealing with identifying, quantifying the linear expression, and at the same time, it will tell us if the relationship between the dependent variable and the independent variable is valid. And probably I should just focus on that right off the bat. The first thing that we have to do is quantify the expression. And so in this case, ridership down here is our dependent variable. Torus is our independent variable. So what we're saying is, okay, to identify the expression is that we have to identify the y-intercept. So in this case, y-intercept is 5.06, and the slope of the line is 1.59. And that's pretty much what I've stated here. Of course, I've written this out, or I should say typed this out. So the expression by itself, the quantitative mathematical relationship for this linear expression is ridership is equal to 5.06 plus 1.59 torus. So intercept 1.59 is the slope. So is that equation any good? Is the equation any good at all? Just because we have the expression doesn't mean that it's valid. We have to statistically prove that it is valid at forecasting ridership. To do that, we focus here on the p-value column, highlighted in yellow. And we want to come down here to the 2.7484e to the negative 0.5. And that simply means that, okay, move your decimal point 5 places to the left. So you can see we would have 0.00002. That is the p-value. And from our previous work, if you recall, that if the p-value is less than the alpha, p-value less than the alpha, we have something that is significant. And let's just assume that our alpha level is 5%. So you can see, or 0.05. So you can see we have something 0.00002 is definitely less than the level of significance, say at 5%. Therefore, we can conclude, statistically speaking, that this equation is good at forecasting ridership when we have the number of torus. So that's pretty much from the standpoint of quantifying the expression, linear expression, and then determining if the linear expression, mathematical equation, is valid. And the validity is based upon the p-value. And of course, going back up here, R squared, the coefficient of determination, is 0.84. And the r square is nothing more than taking the square of your coefficient of determination. So that's pretty much, I think, you can take from the text directly, but hopefully this has been helpful in quantifying the expression and then determining if the equation is valid or not.